All right, recording is rolling. It's Thursday, April 6th, and I have a bunch of activities lined up for you guys today related to electromagnetism. All right, so, do you guys remember? Okay, here. Well, I'm going to have you guys construct an electromagnet, a motor, and a compass using just these materials on your desk. The cups are also involved in the compass. There's a little bit of water there, so I'll put that aside. Okay. And then we're going to do an orienteering activity. So we're going to be outside for about the last half of class, and there is some buried treasure out there. You might see some treasure maps floating around, but if you don't have one, then hang tight because we'll do that later. All right. And so here we go. Um, uh, Let me remind you guys about some physics principles here. Do you guys remember a right-hand rule for electricity? Anyway, we're not torque back in December, but electricity. So here is current measured in amps, magnetic field measured in Tesla, and force measured in newtons. If you have any two of those lying around perpendicular to each other, then the third one will pop up. Right? And well, the first thing we're going to do is actually we're going to construct pretty much exactly this, an inductor, right, which will act as an electromagnet. Right? So it's kind of like if you force a current into a loop, it'll create a straight line magnetic field. Right? Sort of think of it that way. Right? So do you guys see a bolt and a long wire? Now, this might be constructed from last class. If it is, then that'll save you some work. But if not, maybe you possibly have a wire that's about 1 meter long. Just wrap it around and around the bolt. Right, round, around, around. Right. So I'll do it while you guys are doing it. Okay. Okay. Now that sure does look like an inductor to me, right? You guys think that looks like an inductor? Boom. All right. So squish it together like that. Put it near the end of your bolt. Right? You guys got that? All right. We're going around the room here. So I think you're up to that step. Does that look good? All right. Everybody's good? Okay. And now take a battery. If you think your battery is a dud, then let me know. All right, but I think most of these are good. Right? Okay. And okay, get a paper clip ready because this will prove that this is going to be an electromagnet. Like right now, there's no magnetism. See, I put this near the paper clips and it doesn't actually attract. You guys see that? Right. But when you attach the battery to these two leads, right, and the ends are stripped, so you're going to create a complete circuit. Right? Now, don't hold it too long because it'll get hot. But just for a few seconds, it'll work. Right? It'll create a current, and that will turn this into an electromagnet. Let's see if it does. Look at that. Look at that. And it picks it up. Ooh. Look, too good right there. Pick it up. Electromagnet. And as soon as you disconnect the battery, boom, it disconnects. Starts becoming a magnet. Got some permanent magnets down here. Needing for that magnetism. All right. All right. Is that working out for you guys? Are we good? All right. All right. Yeah. What's up? Oh, okay. Let me be right over there. I'm gonna pause this video and check that out. All right. Recording is resumed. All right, how you guys doing? Is that all right? So everybody's good on the electromagnet. All right. Next one. Let's build a motor. You guys ready for the motor? The motor. All right. Oh, here. Let's look at the physics principle here. What is a motor? Right. A motor is converting electric energy into mechanical energy. Okay? So if you have a current running past a magnetic field, that will create a force that's perpendicular to both of those. Right? So what do we need here? We need a current and magnetic field. Right. Well, here's my magnetic field. You guys got a stack of bar magnets? Usually you have CS2 was just a single magnet, but I've got 4 magnets here. That works pretty good, I think. For my right. Oh, guys, the poles of these magnets are on the faces. That'll be important, especially when we build the compass. But I'm gonna put the face straight up. Okay, you see, I got the top magnet right here. Okay. And then now you might have one of these. Do you guys see a loop like this? Right. If you don't have one of these, you might have a wire that's about 30 centimeters long. Right. Who needs materials to make this, or doesn't have this, or can't make this? Okay, so everybody either has this or has a wire about 30 centimeters long. The end should already be stripped. So wind this around in a circle. Now, things you're looking for, you want this to be symmetrical, like balanced, so it doesn't really have a strong preference about which way to hang, right? And here, and to look for that, what you're looking for is for these two leads. Do you guys see if I draw a line straight from lead to lead, it cuts a line straight through the center of the circle? You guys see that? Lead to lead cuts a line straight through the center of the circle. Right. That means it's gonna be pretty well balanced. Is that true for you guys too? Right. Like my leads aren't over here where it would just like always hang down one way. Like this is pretty well balanced. Okay. That's the most common mistake I see students make with this. That's why I'm emphasizing this point. So you guys can draw a line between your two leads and it cuts straight through the center of the circle. Is that true? Right. Now the leads are stripped so they can contact other metal and make the circuit, but the middle is all insulated, so the current will be forced to flow around. Okay. Now, take a battery and a couple of paper clips, and I have my paper clips taped on. You could just hold them on with your hands, but I've got mine taped on. Right. Let me give you guys a few seconds here to catch up that step. So I got my leads taped on my battery. Okay, you guys do get to work with tape today. All those tape dispensers out there. A special day. I've got some tape. Oh, get this. All right. So does everybody have these two components? Okay. Now you guys see what's going to happen, right? Is when you connect these leads of this wire circle to these leads of the battery, it's going to create a complete circuit, right? A closed circuit. Okay. Now, again, don't leave this on here for too long because it'll get really hot during the battery. But for about 10, 15 seconds should be fine, right? So I'll connect this like this. Right. Now notice the metal is touching the metal. The insulation is not touching metal. That would open the circuit and it wouldn't work. The metal is touching the metal. You guys see that? If you put this over your magnetic field, right, sometimes you have to kickstart this thing. This ain't gonna work. Oh man. There we go, right there. Boom. Let's add some more magnets here. Normally it's four is fine, but it's like getting weak or something. There we go. All right. Yeah, guys, and that right there, how long could that spin for? Well, oh, it's kind of spotty right now. Does battery get drained or something? All right. How long could this spin for, ideally? Until the battery drains, right? Okay. Let me maybe try this with another battery real fast here. Pick this up. Got it here. Let's see there. Ooh. Oh yeah, that's a lot better. You guys see that? You guys see that right there? True. All right. And that could go, yeah, exactly, until the battery drains. Boom, there it goes. Right. Right. So you have a current past magnetic field. Right. And the fact that there's an area there, magnetic field through that area creates a flux. And that flux is turning on and off. Right. There's a 1.5 volt difference across these leads. Create a force. Right hand roll, create a force. Right. All right. Let me pause this video again and walk around and make sure you guys are doing all right with the motor. All right, recording is resumed. All right, you guys ready to make the compass? All right, so yeah, walked around, make sure. Looks like all the teams got both of those. You guys are good? We're ready for compass. Now, a compass. You guys know we're in a weak magnetic field right now. We're surrounded by Earth's magnetic field. It's about 5.5 to the 10⁻⁵ Tesla. I think is the value. Right, so really, but strong enough to that these magnets want to align to it. Now, if you just like leave them on a surface, there's too much friction for them to naturally align to Earth's magnetic field, right? But if you could get rid of most of that friction, then they would. You guys have a couple of cups on your desk. You guys see a couple of cups? It might be that one of them already has water in it and one's dry. If that's the case, then you're ahead of the curve. Okay. You guys have one cup with water in it, one that's dry. Does anybody need to fill up cups with water? Right, if you do, go ahead and run to the lab table real fast and put some water in one of these. Okay. All right. Okay, guys, take the dry cup and put it inside the wet cup so that it floats. You guys see that? All right. Here, let me do it again. So you guys have two cups, one with water in it, one with no water. Take the one with no water, put it inside the cup with water so that it floats. You guys got that? Okay. All right. Any question? Any question? All right. Now, magnets. Take 2 or 3 magnets. I'm going to try 2 right now. I'll say. And I need to show you guys where the faces are on these magnets. The poles. The poles are on the faces. So this is either the north or the south pole, and then this is the other pole, or your south or north, right? Right, basically poles on faces. So if I'm looking at it from above, I can see a line. Now I want the pole to be faced horizontally, which would allow them to align with Earth's magnetic field, right? Which is running horizontally, right? So go ahead and put the magnets inside the dry cup. Now you guys know there's no water touching the magnets. You guys got that? Right. And you have the poles face out horizontally. Right. Right. Then let me get these magnets out of the way. Right. Go ahead, drop that there. And you know what? That is not balanced. Let me throw in a third magnet. Actually, I've been doing 3 all day today. It's been working a little bit more. Just wanted to try 2. Right. Let me throw in a third one. All right, third magnet. Boom, right there. There we go. All right, put that there. It's horizontal. You guys see that? Right. Drop it in here. And, well, see, oh, look, it spins a certain way, right? It orients itself a certain way. So there's north, there's south. Okay? And if you give this a rotation, then it will always spin back to its original orientation. Spin this way. Here, get rid of that paper clip right there. Just throwing this off. Okay, and it wants to go back to the way it already was. Look at that. Right? So nice north-south line right there. Right? Right there. Oh my God. All right, pause the scan and walk around, make sure everybody's doing all right. All right, no, one more thing here. All right, recording is resumed. Right, so I gave you guys all this treasure map. We're gonna go outside, and you guys are gonna find and dig up some treasure. But I need to show you guys how to read bearing, how orienteering works. Right? Orienteering and reading bearing. All right, so let me get a compass rose going right here. Compass rose. All right. Got north, south, east, west. Right? The compass rose. Right? Now the first step on here says start at the west end field goal post. We're going to go out to the practice field. So everybody's following along here, right? Because so you guys know where we're going when you guys go outside. Right. So here's the practice field. Here's the building we're in. We're going to come this way. Right. There's a field goal post right here. There's a field goal post right here. The one closer to the school is the west end. The one further away is the east end. Okay. I've always done this activity along with constructing the compass because you could use the compass to orient your directions, right? I found over the years that actually like taking all those materials like the magnets and the cups and the water is like really cumbersome and not very helpful. So what we're going to do instead is treat the field as a straight west-east line, which actually it pretty close to is, okay? Right, so west-east is right here. So this is like the surface of the field, right? You guys got that? Right. Questions so far? All right, so it says start at the west end field goal post. So everybody's starting right there, boom. Right, now what? And then it gives you some directions. Walk so far at this angle, so many degrees. Ooh, what is this? East of north, east of south, west of south. You guys see that? Right. Now, I should tell you guys too, there are different versions of this map, but they all lead to the same location. The reason I did that was so that everybody's not in one giant ball walking together, so you guys can spread out. But tell you what too, the only difference mainly between these maps is just I switched the order of the steps because these are all vectors. Can you add vectors together in different orders and always get the same result? Yeah, you can add vectors together in any order. What that means is you can follow these in order. You can go first, second, third. But you could also, for example, start with the second one and then do the third and end with the first, and it'll end you up in the exact same location. Okay. So if you want to do something like that, then go for it too. Right. So let's see how you read this thing. Say 45. Again, yours may match mine. Yours might have these in different order. That's okay. It says walk 43 meters, 45 degrees east of north. So let me see. What is 45 degrees east of north? All right. So bearing is always relative to this north-south line. So I'm starting on the north-south line. Now, east of north is like somewhere in this northeast quadrant. West of north is somewhere in the northwest quadrant. East of south is somewhere in the southeast. West of south is somewhere in the southwest. That could cover any direction you want to go, right? Relative to a north-south line. So 45 degrees east of north, I'm going to start with my north line. Cut 45 degrees. Bam. Does that look like about 45 degrees right there? Pretty close. Right. So I throw down my ruler, and there's a nice 45-degree line. This is 45 degrees east of north. You guys see that? Right. And then it tells you how far to walk. It says 43 meters in this case. So can you guys track out 43 meters that way? Students are usually pretty good about this. You guys know every meter is about 3.28 feet, a little bit over 3 feet, right? Next step. Now you'll do this sequentially. So you'll pick up from that location and then you go to your next step. It says 47 meters, 30 degrees east of south. So you'll continue from this point. Now, just to simplify this, so my drawing isn't all super cluttered, I'm going to start as if it's from the center, as if this was your first step. Is that okay? Right. So if this was your first step, 30 degrees east of south. So here's of south. 30 degrees east of that is like this direction right about here. That looks pretty close. I should have a protractor, but got what I got. Right. Again, these students are usually pretty good at eyeballing this and figuring this out. Is that 30 degrees east of south? You guys got that? So you start with of south and then go east. So trick off 47 meters. Of course, that was your second step. You actually do this first and then this one. And then there's a third step. So you wherever you're at that point, it says 19 meters, 60 degrees west of south. So again, if this was your first step, you'd say, well, what is 60 degrees west of south? So here's of south, 60 degrees west of that looks pretty close to, I think that's pretty close. This could be 60 degrees west of south. You guys see that? 60 degrees west of south. Right? Right? Everybody good? Right. So you do those steps sequentially. So whichever one you end up, right? You pick up from that point and then do the next one, and then do the next one. Right? Good so far? Right. Right. Now, where the treasure is buried, there is some buried treasure out there. Actually, it's a little treasure box, looks like this. It's got some treasure inside. I staked down actually a shorter version of this into the ground so that from above it looks like this. It's about the size of a dime and it's flush with the ground. Okay, you guys get that? Looking for this stuck in the ground. This is like flush with the ground. Okay, so if you find it. All right. Any questions about orienteering? All right, you guys ready to go outside and find some treasure? All right. Yeah, everybody's been successful so far today and usually in the past too. So yeah, let's head out there, find some treasure, and then yeah, head off into a 3-day weekend. Oh yeah, treasure.